Welcome to Chapter 4. Now that we've spent all these many months learning everything we can about derivatives, we're going to go ahead and undo all of that work by talking about antiderivatives, the opposite of a derivative. So the idea behind an antiderivative is working backwards. If we know that little f of x is the derivative of some other function, which we'll call big F of x, we say that big F of x is an antiderivative of f. In other words, if you can take the derivative of big F and get little f, then big F is an antiderivative, right? Little f is a derivative of big F is an antiderivative of little f. Now we have to be careful here because when we were taking derivatives, you get a unique derivative, but when you go backwards and take an antiderivative, you can get a lot of different answers. So for example, the function big F of x is equal to x squared plus 17 is an antiderivative of the function little f of x is equal to 2x. And I can check that that's true by taking the derivative of this function. What do I get? I get 2x plus nothing. I get 2x. Right? So this big F is indeed an antiderivative of the function 2x. It's just not the only one, because we could say, for example, the function, I'll call it big G of x, equals x squared plus 372. That's also an antiderivative of 2x, right? If I took the derivative of this function, I would get f of x equals 2x again. And the function h of x, which is x squared minus 1, for instance, that's also going to be an antiderivative of 2x because the derivative of this function is 2x. In fact, we're going to get infinitely many antiderivatives because I could just keep swapping out this constant term with anything, and it'll still be an antiderivative of this 2x function because the derivative of x squared is 2x and the derivative of a constant is nothing. But luckily we have this theorem which tells us that's the only way that your antiderivatives can really differ from each other. It says if f of x is an antiderivative of a function little f, then every antiderivative of little f is going to be of the form big F of x plus c for some constant c. In other words, every antiderivative of 2x is going to be of the form x squared plus some constant. Right? You're not going to get any other crazy different types of functions. They're all going to look exactly like this with some constant at the end, and that constant could potentially be 0. So we have notation for this. We would write, this is kind of I didn't draw it very well, this is an integral symbol. It's like a long stretched out S almost. We write that the indefinite integral of f of x with respect to x is equal to big F of x plus c, to mean that the derivative of big F is this little f function, and we would call that this function y equals big F of x plus c the general antiderivative or the indefinite integral of f. Right, let me give you an example here. Right, this notation means the general antiderivative of the function 2x with respect to x. We already talked about this, right? We know that all of the antiderivatives of 2x just look like x squared plus 17 or 372 or negative 1 or 0 or something. So we just write x squared plus c to say that this could be anything, right? This is just a constant. It could be anything. And the derivative of this is still going to be 2x. So we would say that y equals x squared plus c is the general antiderivative or the indefinite integral of the function f of x equals 2x. Okay. And similarly, we would say here, if we wanted to take the indefinite integral or the general antiderivative of 3x squared, we should be thinking to ourselves, what function do you have that when you take its derivative, you get 3x squared? And just from experience of doing a bunch of derivatives, which we've all done, hopefully we know that when you take the derivative of x cubed, you get 3x squared, right? You'd bring the 3 down in front, you'd subtract 1 from the exponent, and you get 3x squared. So the antiderivative of 3x squared would be x cubed, but because we're doing the general antiderivative, or the indefinite integral, we put a plus c at the end. And we say that y equals x cubed plus c is the general antiderivative or the indefinite integral of the function f of x equals x cubed. Okay, so hopefully this makes sense so far. We're really kind of undoing the work of taking a derivative when we take an antiderivative. And just from experience so far, we've been able to try to deduce what these antiderivatives should be. But we have all these different rules and shortcuts that we've learned for taking derivatives, and we can just kind of work backwards to try to figure out what the antiderivative of these different types of functions should be. So let's talk about the power rule for integrals. These are indefinite integrals, right, or antiderivatives. So if we want to find the antiderivative of the function x to the n with respect to x, I know that that exponent's going to have to go up 1, right? If this was x squared, if the derivative was x squared, then the antiderivative, right, the original function, should be some sort of an x cubed function. If this was a 5th power, then the original function should be a 6th power, because when we take the derivative, the exponent goes down by 1. So when we take the antiderivative, it should go up by 1. But we also need to account for the fact that when we take the derivative of this, we would be moving that old exponent down in front as a coefficient, and we don't see that here. So to sort of correct for this, we have to put a factor of 1 over n plus 1 out in front. And of course, anytime you're doing an indefinite integral, you put a plus c, because you could have a constant added at the end here. But this is what the power rule for integrals says. It says the antiderivative of x to the n would be 1 over n plus 1 times x to the n plus 1. And if you're not convinced by this, we can check it. Right, let f of x, big F of x, the antiderivative, be 1 over n plus 1, x to the n plus 1, and we can check, plus c, that when we take the derivative of this function, we should hopefully get x to the n back. Alright, so let's take this derivative using the power rule. We'd multiply the coefficient times the old exponent, and we get that f prime of x, the derivative, is going to be 1 over n plus 1 times n plus 1. That's n plus 1 over n plus 1. Times x to the n plus 1, the old exponent, minus 1. That's going to give you an n. And then the derivative of a constant is just 0. So we get that f prime of x is just x to the n, which is exactly what we wanted, right? We want the derivative of this to give you this, and it does. Right, as another simple example, if you wanted to take the indefinite integral of x to the 7th power with respect to x, the power rule tells us that what we need to do is we need to add 1 to the exponent, so x to the 7 is going to become x to the 8th, and then we need to pull out a factor in front of 1 over 8. And then at the end, we always add a plus c. Right, and you can check that when you take the derivative of 1/8 x to the 8th power, you'd multiply 1/8 times 8. That's just going to give you a coefficient of 1, and then you subtract 1 from the exponent to give you that x to the 7th. Derivative of c is always 0. So this works out as well, right? So the power rule for integrals is really just showing you how to go backwards from the power rule for derivatives. So let's try to use that here with some more examples. I'm going to give you a really big polynomial here and ask you to find the antiderivative. So we start with this original function, 3x to the 5th plus 10x to the 4th, blah, 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 this whole thing. And we want to take the antiderivative of it, right? This symbol out in front says take the antiderivative, also called an indefinite integral. Now, what makes this a little bit more complicated than the power rule for integrals that we saw up above is that these all have coefficients on the outside. But just like before, you can kind of pull those coefficients out and just sort of keep them as we go. So if we were to try and take the antiderivative of this, right, leave the 3 on the outside for now, and then just take the antiderivative of x to the 5th power. Right, according to the power rule, I need to increase the exponent by 1, so that'll be x to the 6th. And then I also need to multiply by 1 over the new exponent. Right, 1/6 x to the 6th is the antiderivative of x to the 5th, and the 3 just sort of comes along for the ride. Right, do the same thing for this next term here. Keep the 10 on the outside for now, and take the antiderivative of x to the 4th. We need to add 1 to the exponent, so that'll be x to the 5th power, and then we need to pull out a factor of 1 over the new exponent out front, so 1/5 here. And you can check the derivative of 1/5 x to the 5th is indeed x to the 4th. Continuing in this way, keep the negative 7 on the outside. The antiderivative of x cubed would be x to the 4th times 1/4. Okay, keep the plus 3 on the outside. The antiderivative of x squared would be x cubed times 1/3. Okay, keep the 12 on the outside. The antiderivative of x, okay, here, remember we need to increase the exponent by 1. Currently we have an x to the 1 power, so now I'm going to have x squared with a 1/2 out front. The antiderivative of 5, now we want to be real careful here because this is like saying 5 times x to the 0, right? I don't have any zeros here. When I take the antiderivative, leave the 5 outside for now, I need to increase 1 on the exponent. So that x to the 0 is going to become x to the 1, and then multiply by 1 over 1 out front. Okay, that's not going to change anything. And in the end, we always have to put a plus c. Okay, cool. So let's actually go through and simplify what this is. Multiplying things through. In our first term, we have 3 times 1/6. We can kind of cancel out a factor of 3 here and just be left with 1/2 x to the 6th power plus 10 times 1/5. We can cancel out a factor of 5 and just be left with 2x to the 5th power. Here, 7 times 1/4 doesn't give you anything nice, so just write it as 1 fraction, 7 over 4, x to the 4th, plus 3 times 1/3, this cancels out, and we're just left with x cubed, minus 12 times 1/2 is 6x squared, plus 5x to the 1, and finally plus c at the end. This is going to be your antiderivative right here. And you can check that this is correct just by taking the derivative of this function. Right? If I call this the antiderivative, if I call this big F of x, if I did it correctly, then when I take the derivative of big F, I should get back the original function right here. Let's check and make sure that that actually happens. The derivative of this would be 1/2 times 6 is 3, x to the 5th power, plus 2 times 5 is 10, x to the 4th power, minus 7/4 times 4 would just be 7x cubed. The derivative of x cubed is 3x squared. The derivative of negative 6x squared is negative 12x. Derivative of 5x is 5, and the derivative of a constant is 0. And checking up above, we see that that's exactly what we started with. That's how we know that we did it right. Okay, but this is what we're looking for. This antiderivative right here that I've boxed off, that's what we were looking for. Okay, now number 2, we want to take the antiderivative of 3 times the square root of x minus 5 over x cubed. Now we're still going to use this power rule, and I probably should have said this before. The power rule is going to work for any exponent as long as your exponent is not equal to -1. We'll talk about why in the next video. But I could rewrite this original function here, right? Find the indefinite integral of 3x to the 1/2 power by rewriting the radical as a fraction root, minus 5x. If I wanted to bring this up to the top, I'd have to change the sign on the exponent, so 5x to the -3 power. We're going to take that antiderivative with respect to x. Using the power rule, what do we get? Notice, once I take the antiderivative, I can stop writing the symbol here. So that's why I stopped writing it at this step up above, and I'm going to stop writing it here. All right, so to take the antiderivative, I need to add 1 to the exponent. Here, let's leave the 3 on the outside for now. Leave the 3 outside. Add 1 to the exponent. 1/2 plus 1 would be 3/2. And then I need to multiply by 1 over 3/2. Right, just like we did up here, you multiply by 1 over the new exponent. Okay? Right, then for the next term, keep the minus 5 outside for now. Add 1 to your old exponent. -3 plus 1 would be -2. And then multiply by 1 over the new exponent. Multiply by 1 over -2. And anytime we take the antiderivative, we put a plus c. Okay, now rewriting this, I'm going to keep this outside for now. Keep in mind that 1 over 3/2 is the same as 2 over 3, right? We can just take the bottom and flip it, have 2 over 3, x to the 3/2 power, minus -5 times a -2 is actually going to give you a positive coefficient here, 5 over 2, x to the -2 power, plus a c. And now I can simplify this just a little bit more to get 2 x to the 3/2 power plus 5/2 x to the -2 plus c. That's going to be my antiderivative. And just like before, you can check that this is correct by taking the derivative of this function and making sure that it matches what you originally started with up here. So let's check that. If I were to take the derivative of this, I would get 2 times 3/2 is just 3. X to the 3/2 minus 1 is 1/2. Plus 5/2 times -2 is going to give you a -5. X to the -2 minus 1 is -3. And the derivative of a constant is 0. And we see that it does indeed match what we started with. Right, so we can check our work and it still matches, so that's good. All right, in the next video, we'll do a few more.